Good morning, everyone, and thank you for joining us. My name is Francesco Pagliarello with Viavi Solutions Sales. I want to thank you for joining our call today on Tetra testing requirement and best practice. We have a lot to share with you, but before we begin, this webinar is being recorded and it will be available for you to review or share with your teams in approximately 20 or 48 hours. We will send an email to all the attendees with a link with the recorded version. All lines are on mute, but we are monitoring the chat and will answer questions at the end of the webinar or reach out to you individually to ensure that you get the answer you seek. The question will be anonymous. And now I would like to turn it over to our speaker today, Barry Hack. Barry.
Thank you, Francesco, and good morning, maybe good afternoon for some of you, and good evening. I know there's others joining from Asia as well. So this is, I think, seminar number 4 in our series. It's a new month, it's a new financial year for Viavi, so it's a fresh start for everyone. And today we're going to be talking about Tetra testing and best practices. So I'd say my name is Barry Hack. I'm a solution engineer for Viavi EMEA region. I've put up the other, shall we say, specialists around the world. So anyone outside of the region can contact those guys. But please, if you're in EMEA, you come through to Francesco, who did the announcement earlier, Hamish, if it's Europe North, or myself for technical questions. I apologize if it jumps back to not full screen. I've had this all the way through and I still haven't worked out. It's called technology issues. Okay, so just a very quick introduction to the company. Viavi started in 1923 as part of Wandel and Golterman, migrated through JDSU and then rebranded as Viavi. And along the way, they've picked up some other businesses. Including, importantly, in 2018, the Avcom and wireless businesses that were part of the Cobham group in the UK. Focusing just on the radio test set side, so this is my history as well as many of my colleagues. I started life with Marconi Instruments, which then became IFR, part of IFR, which then became part of Aeroflex, then part of Cobham, and then into Viavi. And along the way as well, we picked up companies like Wiltec in Germany, and they had very good testers. And then Celerity Systems in California, who were doing more broadband capability, which was more military, shall we say, orientated. Okay, Viavi itself as a large company, multi-billion-dollar company. We're around about 4,000 employees now. We like to be number 1 in our markets, or a very close number 2. So in our segments of test and measurement, wireless and avionics, we are number 1. But interestingly, Viavi is also involved in optical capabilities. So we produce most of the anti-counterfeiting ink, shall we say, for most of the world's banknotes and security seals on things like your Xbox. But also optical capability on phones. So if you see modern phones that may have 3D cameras or 3D facial recognition, a lot of that optical filtering and lenses will come from Viavi. Okay, so we're not just radio test sets. Today I'm going to talk about Tetra. I'm going to focus on the 3920B because it has most capability of the three units, but I will also touch on 8800 and 3550. We'll talk about manual testing of radios, and by radios I mean portables and mobiles as well as base stations, and then I'll be going through some of the automatic test capability as well, and maybe the benefits of that for the customers. Okay, saving time, de-skilling the process, repeatability, and cost saving. So why is it essential to use a modern radio test set? So I've just got a little picture there of some Tetra measurements running. You know, in analog and digital systems, we want to check the frequency of the radio is correct. You don't want to be off channel. If you are, you may have problems between the transmit and receive link, or you may be causing interference to other users in neighboring channels or neighboring systems. Again, I apologize why it jumps back. We want to measure power. In analog, typically, AM and FM systems, your power is easily defined. You have an AM envelope or you have a constant power if it's FM, for example. Of course, you could have pulse signals, radar, for example. But in digital, a lot of the systems, the power is, shall we say, non-linear over time. It is moving in sympathy with the modulation in some way. You'll also have, most of these systems now, you have multiple time slots. So you could have, for example, DMI, you could have 2 users on a channel, Tetra 4 users. And even if we jump back to good old GSM, there was 8 users on a channel. So measuring your actual channel power is important, rather than all of the power of all of the time slots. And again, with an analog meter, it would not be able to handle this very well, because it would probably be doing some sort of averaging over time. So your power would read too low, or it'll be doing a peak measurement. And in that case, your power read could read too high, because you'll see with Tetra that the power actually goes over, shall we say, a magnitude of 1. And analog, we'd look at modulation, so we'd look at maybe the AM or FM performance, and we could look at the FM deviation or the AM depth, for example. Very different in digital, we have different measurements, for example, error vector magnitude. And then in both cases, again, we need to look at the receiver as well, and we look at sensitivity. So an analog would maybe measure SINAD or SNR, for example. But in digital systems, typically we're measuring the error in a digital bit stream, so the bit error rate. Some other things we'll measure in digital, I've already mentioned the modulation error as an error vector magnitude. For Tetra, we measure both the peak value and the RMS value. They are both specified. The burst timing, so we need to make sure that we are transmitting at the right time for our time slot, so we're not interfering with the other users on our channel. And we also have to measure the residual carrier or magnitude error. So residual carrier is a measurement of how much, shall we say, local oscillator breakthrough has gone onto the output signal, or how much of the unmodulated signal has broken through the modulator and got transmitted. And then magnitude error might be where you might expect the amplitude to be at a certain value. For example, on DMR systems, it would be fixed. On Tetra, it's not. But you'd be looking to see how the power is deviating from the nominal ideal situation. So there's a lot of extra measurements we need to do in the digital system, and the analog test sets cannot handle most of these. Importantly, the digital test sets do handle the analog measurements. So you obviously can still do analog testing as well. So that's a little bit about what you need to do. And now we've just got one single poll question we want to give you and ask you what you think are your priorities. So over to Jack and Francesco for a moment.
Yes, we are getting some answer. We are around 50% of the voters. We take a little bit some minutes. We give some additional minutes. Please provide your answer. One more minute and then we close the poll. Okay. Okay, we have the result of the poll, Barry. We have 83% audio quality, 76% connectivity, and then 50% safety feature, and then the other two are user experience and build quality.
Okay, that's good. That's useful information for us for what we're doing now and what we'll be doing in the future. So thank you everyone for that. Hopefully you can now see my presentation again. Is that working okay, Francesco?
Yes, we are working.
Perfect.
We see the Tetra physical layer. I can see it.
Fantastic.
Thank you. There.
So just a couple of slides on the technology before we break into the actual testing. So Tetra is a system we call pi/4 differential QPSK, which I'll explain in a little bit more detail in a moment. Each channel, which is a 25 kilohertz channel, has 4 time slots. So basically, we digitize. Apologies again. We digitize the voice, or we take the data that you want to transmit, and we basically compress that so we can transmit it in a quarter of the channel time, shall we say. So you can have 4 users all working on the same frequency channel. It can be a full duplex system, so you have up and down transmit and receive channels, and you have a corresponding time slot in the other side of the radio link. We're transmitting 2 data bits per symbol. That's not, for most people that doesn't really matter. We don't need to look at that in that detail. But what's interesting is if you think of 4 time slots or 4 users in 25 kilohertz of bandwidth, your effective bandwidth use is 6.25 kilohertz, 6.25 kilohertz. Okay, so if you assumed you were using a channel all the time, the effective bandwidth is 6.25 kilohertz. Compare that to DMR, you have 2 users in 12.5 kilohertz. Again, effective bandwidth is 6.25 kilohertz. Okay, so if you look at some of the other digital systems out there, the effective bandwidth is equivalent, 6.25 kilohertz. That is very, very different to an analog system where historically the channels were 25 kilohertz for 1 user, maybe 12.5 kilohertz. So you can see how we've compressed a lot more people into the spectrum. That is no different, the same requirements that we had for cellular, taking the old analog original cellular systems and converting those to digital to compress things and get more people into the same space, the same piece of spectrum. Now, any signal can only have 3 components. So any signal known to anyone in the world is either going to have amplitude, frequency, or phase. And remember, frequency and phase are related to each other over time. But if it was an analog AM system, we wouldn't touch the frequency and phase. We would just change the amplitude. If it was an FM system, we would leave the amplitude fixed, the phase fixed, and we would only change the frequency. Now, interestingly, for Tetra, as an example, we actually change the amplitude and the phase. So now we've moved to 2 dimensions at a time, which instantly gives us a 2 times improvement in, shall we say, channel efficiency or spectral efficiency. You'll see better drawings than this when we actually look at the test set and the analysis. But you'll see in this picture on the right hand side, there's actually 8 points. But at any one timing point, you can only be on one of 4 of those points. And we always in time, every time we send a symbol of data, or the 2 bits of data, we rotate by 45 degrees plus the difference depending on the data symbol. So you see we never stay on the same point. We never go through the center. That makes it easier for the amplifiers. They don't have to be so linear in the radios. If they're not so linear, it means they can be made cheaper, or shall we say more cost effective. So there's particular reasons why Tetra is chosen with this type of modulation. Okay. Now the drawing there is a little bit inaccurate, because that is just a mathematical perfect signal with no filtering. You'll see on the real signal we go beyond those points. So as you go in and out from the center, you're changing amplitude, and as you go round, shall we say, the circle from the real axis, we're changing the phase. So rotation is phase, and in and out, or amplitude from the center, is the amplitude of our signal. But on a real system, you'll actually see we go past these points, those 8 points you see on the outer section of the star shape. We go beyond those, shall we say, magnitude 1 points because of filtering. And that can be quite important to check for compression, for example, in amplifiers. I've seen other equipment, even our Wiltec testers, they would show a drawing similar to this, but what you could be missing then is seeing any compression in those amplifiers, which you would see, for example, on the 3920, 8800 and 3550 test sets. I'll show you the picture in a little while. Remember I said Tetra is a bursted signal, a TDMA system, so time division multiple access. So we have to be quiet, not transmit until it's our time slot. And when our time slot comes, we have this T1 time to ramp up. T2 is when we actually transmit the useful data, and T3 is our time to ramp down. And those hard blue lines will be our physical time slot. And we have limits on the timings. We have limits on where the power can be in each of those 3 regions. And it's great that we can measure all that automatically on the testers. There's many types of calls we can make on a Tetra system as well. So for GSM, for example, you would only make a call from a GSM phone to another GSM phone, or from a GSM phone to a landline, to a house phone, for example, or vice versa. With Tetra, there's many different calls. One-to-one calls. You might do calls through the network. You might do group calls. You can still do obviously telephone type calls to an external telephone system outside of the Tetra network. The calls can be made by the radio itself, or the network can call the radio. You might make emergency calls, all sorts of things like that. And if any of you have done an emergency call on a cell phone, you'll see typically it's a number of seconds to make an emergency call. With Tetra, the requirement is 300 milliseconds. Okay, for emergency calls, and typically that is held for all other types of calls. But there's many times we've seen calls take a lot more than 300 milliseconds. We've actually recorded an emergency call that took 13 seconds, just under 13 seconds to make, which is unacceptable if you're in an emergency situation. So looking at the 3920B, there are 3 main operational modes of the test set. One is what we call MS testing. So we're testing the mobile station. So that would be portables and mobiles, for example. Could be modems as well that are on a network. So if you have, say, a water company, I've done work with the Panama Canal in Panama. They have a lot of modems monitoring things on the canal. Could be water levels, could be water temperature, and those modems are also reporting back information on the Tetra network. We have the Tetra BS, or base station test option. That's for testing the base stations, either live or in test mode. We have the Tetra direct mode capability. So that's when the portables and the mobiles are not using infrastructure, but they're in effectively a walkie-talkie, local walkie-talkie mode. And there's another option there, an extra option, energy economy mode, which I think typically only Motorola use on some of their networks, but effectively it allows us to make the radio go to sleep for some numbers of milliseconds or seconds and then wake up again to check if there's anything on the network for them. And that's useful if you want to conserve a little bit of extra battery power on those portable radios. So what's so great about our testers? We've been involved with ETSI since it started. I think my first time with Tetra was 1993, when I was developing our Tetra signal generator in the Marconi days. We've been members of ETSI, I think, ever since, and we wrote most of the test documentation for the ETSI standard. So that's come from Viavi and its historical companies. Okay. You might find other equipment that just uses a control channel. So you have a control channel which the radio will register onto the network, and then there's three other time slots available, and you can use one of those for your call. We can allow you to do that, or what we do, which is more typical on a real system, is we use the control channel to make the registration of the radio and command it into calls, or command it into an emergency mode, or command it to send a status message. But then for the actual voice traffic or data traffic, we will actually tell it to use a different channel, a traffic channel. So we test the radio in its real functional mode of both control channel and traffic channel, not just using one frequency and one control channel and nothing else. That can be quite important to check radio capabilities. We support all of the different Tetra call and messaging modes, all the call types, messaging modes, the SDS messages, status messages, and if it's SDS messages, all the types 1 to 4. We support the T1 test mode and T1 RF loopback, if you have access to that, which I'll explain in more detail. But we also support the Tetra TT registration and loopback, which typically is used by Airbus radios. Okay, whereas T1 would typically be used by the likes of Motorola and some of the other players. We have auto test only for mobile stations. That's only for portables and mobiles. Do not confuse that with auto test 2, okay, which has even more capability for all systems. So auto test is something free you get with Tetra MS, but we have auto test 2 for all of the Tetra systems. And Tetra interoperability compliant. So again, historically, we were always the referee when two companies were arguing over whose fault was it that their radios didn't talk to the infrastructure. So we would be the guys in the middle that would make the decision for ETSI. Interestingly, when you set up a Tetra MS system on the 3920B, there's quite a few parameters you need to set up before the radio will work, and this is partly for security of the radios and live networks. You have to pick, you see on the left here, you have to pick the right frequency channel. So we have the standard channels are all in there, both in terms of frequency, and you can have some kilohertz of offset or not. So for example, in Europe, we would use Tetra 380 plus 12.5 kilohertz for the emergency services. Whereas in the Middle East, typically it would be Tetra 380 with 0 offset. And then the commercial services tend to be in the 410 and the 450 megahertz range. 800 megahertz systems for Asia Pacific, typically. We allow you to make your own systems. You can set your own channel plans up, or you can default back to just frequencies, just megahertz. You don't even have to have channel settings. You can just use good old megahertz. On the right-hand side, we have to set up the country code, network code, base color code. That's important along with that channel plan or frequencies, because without any of those being set correctly, the radio will never register on the base station, and it's seeing the base station as a live network. Okay, so same as a live network. If your radio doesn't see its network that it's programmed for, it will never register. Okay, And there's some other parameters on the right-hand side, which I'll touch on one of those a little bit later. Okay. So Tetra transmitter tests, we might want to look at frequency error. We might want to look at the transmitted, I call slot power. You might want to look at the power steps. You might want to look at the digital timing error in the system because it's got timing, and you might want to look at the EVM, peak and RMS. Now, we have a lot of capabilities. So the little picture you see to the center left, that shows you some of the capabilities we have for measuring the modulation accuracy. So the first three measurements, vector, phase, and magnitude, we'll do that over time. Trajectory shows the 8 points, but all of the frequency and amplitude, phase movement in between. Constellation would only show the 8 points when we're taking the timing measurement to get the correct decode for the ones and zeros. But what I'm showing on the right-hand side is something called rotated vector. So this is something we introduced many years ago, and it's very, very useful for both engineering and service personnel. Because what we do, we actually take the constellation points. So you physically only have 1 in 4 points active at any one time, but on the screen you would see all 8 points. So the computer can work out which point we're at, but for humans it's too quick. We just see all 8 points. And what we do for rotated vector, we actually mathematically map them, rotate them onto 1 point, and that allows us to see some key issues with the radio graphically, as well as to the left of that picture, you see all of the numerical measurements. Okay, and that's just a sample of some of the numerical measurements we can make, and we can color code them. Everything's green, everything's passing. We would probably have a good radio, at least on the transmitter side. Now, above that picture on the right, you'll see something in red. Okay, if I see a screenshot like this, the first thing that goes in my head is they're doing the measurements wrong. What are they doing wrong? Okay, they haven't included any cable loss compensation. So again, typically from a radio, you will have a cable from the radio, maybe 50 centimeters or 1 meter if it's a portable or mobile, connected to the test set. It may be 5 meters if you're connected to a base station. And it's important that you add that cable loss into the measurements, because if you don't, if you're transmitting 1 watt of power plus 30 dBm, we will measure that maybe as plus 28 dBm. Okay, so you could fail the power measurement, or you could tune the radio and assume the test set is perfect, set it for 30 dBm, but you're actually pushing 32 dBm out of the radio. So instead of 1 watt, the radio is now pushing 1.5 to maybe 2 watts of power, which could break your license agreement, and it could also reduce your battery life and talk time. On the receive side, the same. If we put a level out of the generator, here I'm showing minus 80, with no cable compensation, if I lose 2 dBs, my receiver would see minus 82 dBm. No problem at those power levels, but it does become a problem when we get to receiver sensitivity. So again, you could fail a good radio on sensitivity because you did not include the cable loss. Okay. So let's jump on. So the picture on the right, just to show you some of the different call groups, call types we can make, and you can define your own call types as well. Okay, I tend to use a phone call when I'm doing calls, because with the different call types, really, you're testing different, shall we say, software features in the radio, and there'll be some guys that Airbus, Motorola, Leonardo, whoever's making these radios. There'll be people in engineering that have spent millions of dollars, millions of euros checking that software. So normally I'd normally do just one call type. I use a phone call, because once it's in the call, I don't have to keep pressing the push to talk button. Okay, you might want to try an emergency call. If you do that, do it from the test set to the radio. I always warn people to be very cautious, very careful if you try to make an emergency call from the radio to the test set. I've seen numerous cases where we've had a radio connected to the test set, but the base station is close by and the radio jumps off to the real network because it is much stronger. The user doesn't see that, they press the emergency button and you can have a major incident. So I was in an oil refinery in the Middle East some years ago, and we were doing this, and one of the users pushed the emergency button, and I immediately knew what had happened because the test set wasn't doing anything and the refinery went into lockdown. So high security lockdown. It did not reopen until they found the cause, which was us, and they cleared that, and it went to the senior management at the refinery to authorize the reopening. So you can imagine the cost to a chemical facility, a military base, a police headquarters, anywhere, if you press that emergency button and it goes live on the network. So be very careful with emergency calls. I've embedded some videos in here. I will run a couple of them and jump through them. So when you download the presentation later, or if you want the presentation, you will get the video, but if you want the presentation, the videos are embedded inside that. So I'm going to jump over some of this, okay, but I'm basically making a call. I can use talkback, test tone, and silence. So if I talk into the radio, go, hello, this is Barry, in the earpiece, a few seconds later I hear, hello, this is Barry. So I can hear the voice come back, or I can do a 1 kilohertz tone, so I hear, or I can just have silence. I can change my measurements. I can change statistics on those measurements, and I can reset them back to ETSI default limits, both normal limits and extreme limits. Okay, so there's two definitions in ETSI. Here you can see I'm looking at transmitter measurements on the left. I'm looking at the power ramps on the right. Now I'm looking at the whole power profile on the left. So the ramps are just those little bits at the start and the end. Now I'm looking at the vector signal. You see we don't go through the center. As I said, that makes the amplifiers a little bit cheaper to produce. Okay, I can look at what's been happening with the test set all the way since I first powered up the test set and registered the radio. So as you go down this, it's registered. I've been making different types of calls. Okay, it tells me the parameters of those calls. You saw I was in talkback. I went to the 1 kilohertz test tone, back to silence, etc. So everything is recorded, and you can extract that or export it from the test set. Okay. So if we talk about the transmitter measurements, I've shown you a quick video there. I've shown you a slightly different picture here, which I'll touch on in a moment. But the measurements are broadly similar, whether the radios are portables and mobiles in what we call MS mode or trunked mode, whether they're portables and mobiles in direct mode, walkie-talkie mode, or whether they're base stations. Okay, either off air or even in test mode, you will get similar type measurements or similar looking profiles. Now, interestingly, what you see on the right on the power profile, you see, if you look at the graphic on the right hand side, the profile ramps, I'm not sure if my mouse is showing up, but you see a big spike and it drops down again, then it ramps up very close to this line, which is the limit. And then this will be the useful part of the burst. And in this picture, because I'm only showing the ramps, I've chopped out most of the useful part. And then the ramp down is very quick, right on that timing limit edge there, and drops down. And the spike you see at the start, that is because there's like an RF kill or an RF on off. So we turn the RF on, and then when it ramps up close to the edge, that's typically these days actually profiled in the software. So in the DSP software that controls the power level, that is actually software programmable. So this manufacturer, and many of you probably know who this is. I could see this picture and tell you straight away what radio it was, even if you didn't show me the radio. That's a feature of how they do their radios, and the reason they ramp up very close to those inner edge limits is to try and conserve an extra few percent of battery. An extra few percent of battery is extra talk time. That could translate into 30 minutes of extra talk time from the battery. That can be very useful. For example, if you're a police officer or paramedic and you're using the radio for 8 to 12 hours. Okay. What you see on the left-hand side, that rotated vector now is very different to what I showed you earlier. It's sort of in the middle of the circle, but it has like a little tail that goes down towards the left-hand side. Oops. And again, that's a feature that relates to that power ramping that you see on the right. So again, the graphical pictures are quite good to see features, but you'll always drop back to the actual physical numbers, and if they're green or red or blue, to see if the radio is passing or failing. Okay. Another thing we might want to check is the power control on the radio. So the radio just doesn't transmit full power all the time. It would in direct mode, in walkie-talkie mode, which quite often is a fallback method if the network is down, in an emergency situation. Some people purely use the radios in direct mode, in walkie-talkie mode. They have no infrastructure. But if you do have infrastructure, typically what happens is when you register on the network, one of the parameters you get sent by the network, if you see over here, is what's called the access parameter. And here it's set as -45. Okay, so the radio will then transmit back based on that access parameter the network has given it, and what the radio's receiver is measuring in terms of the RSSI, or its received power. So as you move away from the base station, the RSSI becomes a more negative number. So in fact, the TX power would ramp up. Okay. So the lower limit of that transmit power is +15 dBm. It doesn't go lower than that. And the maximum is whatever the radio can do, or what will take priority over that is the maximum TX level. Again, that is a parameter down here that the network will tell the radio when it registers. So by default, we set that to 1 watt. So even if you had a 1.8 watt portable or a 10 watt mobile, on this network, on my base station, which it sees as a live network, the radio should never transmit more than 1 watt, because that's a command that I've given it. So now we're bounded in this case by +15 dBm as a minimum and +30 dBm as a maximum. Okay, and we always jump in 5 dB steps. So power control is quite an important issue because it's all related to battery life and talk time. So that's quite important. Okay, and it's what's called mobile assisted power control. Okay, some networks will command the power for the radio, but typically on the Tetra systems, the radio will make the decision on what it will transmit back. We can support both modes. Okay. I talked about the rotated vector and how we take those constellation points and we mathematically map them onto one point. Remember, as we go in and out, its amplitude, as we go around the circle or the arc, its phase. And here's 3 examples. So the first one, which looked a bit like the screenshot you saw on the radio, where it ramped very close to the edges on the time slot, that can be related to burst timing. The second one in the middle, you see sort of four distinct points inside the red dotted circle, and then some other points that seem to be going around the edge of the arc or the circle, which is phase. Okay, and then on the right hand side, you see 4 little lines almost close to the center point of that green circle. So that's carrier leak with a little bit of phase noise. Okay, bear in mind the green circle is actually the test limit. So all these radios are good, but what you're starting to see here are features of the radio. Okay, and carrier leak, for example, could be poor design is probably the wrong word, but it could be tracks on the circuit board that are close together that are cross-coupling signals, or quite often what carrier leak becomes is poor screening. So if you have metal cans to screen different parts of the RF circuit, if the screening is not very good or there's some corrosion on the screening interface to the board, or there's holes in the screening can to let out the heat, that can all lead to carrier leaks, so unmodulated carrier getting through onto the transmitter output. So these pictures are always very, very useful. For receiver tests, okay, we can test base stations, mobiles and portables in two modes, both T1 and TT loopback. So we don't just support the T1 mode, we also support TT loopback. The difference being with T1, you actually put a test signal into the receiver and the radio or a computer on the back end of the radio will measure the bit error rate. With TT loopback, the radio basically places a call with us and we send it a known data stream, it loops that back to us, and then we recover the data stream and we measure the bit error rate on the test set. And we can also do direct mode testing. For the MS T1 testing, we support all of the Tetra T1 test modes. So we say in terms of the different test signals, but typically people will use a type 1, which is what's called a 7.2 kilobit traffic channel. Well, that's what it's emulating. Okay. If the radio supports T1 loopback, we can support that. In which case we could do the bit error rate measurements for you. You see on this picture here. Most radios don't do that. Most radios you need manufacturer software to be able to do the T1 measurement. And importantly, most customers do not have access to that software. Okay. And in some cases, the manufacturer's own service workshops do not have access to that software. So therein can lie a problem when you want to do receiver measurements. Okay. So you can either get the bit error rate measurement on the screen on the radio. I don't see that very often with Tetra. You use the manufacturer's software. And when I talk about tuner software, I'm not talking about software that's available to the customer base. I'm talking about very tightly controlled software that's only allowed to be with engineering or high-level OEM service centers. You may have engineering software, and the case I have engineering software from the manufacturers, which they don't release to anyone else. In fact, one of the big companies, I don't think they've even released it to any of our competitors. So we're in quite a privileged position. So this is an example of one of those manufacturer softwares that I have. So I can measure both receiver or RSSI receive signal strength and the bit error rate, okay, as well as other parameters. It becomes a problem for most customers though, if you don't have access to it. For TT loopback, this is typically used of Airbus. If you go back in history, originally it was Nokia, then went EADS, Cassidian, Airbus. And TT loopback method is effectively the same method that was used with GSM and 3G. So that's why Nokia implemented it. Unfortunately, it's only an optional method in the standard. T1 is mandatory. TT loopback is optional, so only Airbus have implemented it, I believe. But in fact, for us as users with test sets, it is a much preferred method because we do now have the capability to do the measurements. Okay, and they would come up on the right-hand side here once we have the radio in TT loopback mode. Okay, so for example, you would key when the radio starts *#5667#. I don't think that's secret. That's actually the 5667 translates to loop for loopback. And on the test set, once the radio registers, you must press this test mode confirm button within 30 seconds. Otherwise, the radio will fall back into normal operational mode for security reasons. Okay. So radio receives the decoded data, and at sensitivity level, that may decode that with some errors. It will transmit all of that back to us at high power. So we don't add any errors to that, and we would then present that on the receiver measurement screen. Okay. For base station Receiver measurements. So now we're in the Tetra BS T1 mode. Again, we support all of the ETSI standard payloads, shall we say, test payloads. And again, just like for mobiles and portables, we used a T1 Type 1. For base stations, that's equivalent is a T1 Type 7. Again, it's emulating a 7.2 kilobit traffic channel, but we do support the other payloads as well. Okay, so typically, I think most, if not all, the manufacturers are using the T1 Type 7. But again, the radio receiver, so not us, usually it's the base station receiver that's measuring the bit error rate. Okay, and again, we'll use manufacturer software for that. Now, importantly, for the base stations, we also need synchronization. Okay, so we have off-air or what we call auto synchronization, which the likes of Airbus, Leonardo, we could put in there. We could add, DAM, Hytera, Teltronic, those type of people. Or the other method is to use a pulse sync method of synchronization. For example, Motorola. So here the base radio will, on the service cable, provides us with a BNC connector that gives us a pulse every Tetra multi-frame every 1.02 seconds. Okay. There's an example of the measurements you'll see on the computer connected to the base station. Okay. For direct mode, again, you can do something with the radio, but guess what? It's the same receiver as you have in the MS or trunked mode. So the receiver is the same. We've just changed how the software works. So the bit error rate should be identical. But just like in the mobile mode, if you place a call in direct mode, you can actually use the 1 kilohertz test tone. And as that breaks up, so you're at minus 80 dBm, maybe you hear it's 1 kilohertz, but at minus 112 dBm or minus 115, you hear, and you hear it breaking up, and that's an approximation of the radio sensitivity. Not exact, because you need to measure bit error rate, but it's a good approximation. You can also use messaging, text messaging or status messages. You keep lowering the level, you keep sending messages, and once a radio fails to receive the messages, you've hit sensitivity. Okay. Just to touch on the base station testing for a moment. I've picked on Motorola because I actually have a Motorola base station at home at the moment. Base stations are much harder to carry around than portables and mobiles. Typically, we'll do a direct connection to the base station. For Motorola, we would use the pulse sync. Okay, but something to consider. Okay, so the test sets have a maximum power input. So 125 watts for a period of time, or 50 watts continuous. The 3550R, the portable unit, is 20 watts continuous. So now you have to be careful. If you have a base station with one radio and it transmits 40 watts, you can damage, for example, the 3550R. So you need a power attenuator before you put the signal into the test set. But even if you have a 3920B, you go, well, it's 40 watts. I'm testing a radio with 40 watts. No problem, it can handle 125 watts. Be careful. If you have an MTS4, which has 4 base radios, if 3 are left in operational mode and you put 1 into service mode and they all come out of a single TX port, you've now got 4 times 40 watts, which is 160 watts. Okay, so if you're going to do this, be careful. You may need to use a power attenuator, or you may need to unplug the power from the other 3 base radios just to make sure you stay within the safe power limit. And even when you've got a single 40 watt radio, Tetra, as I said, the amplitude goes above a nominal magnitude of 1. So you don't see this in some other test sets that just show the graphical, shall we say, constellation diagram or vector diagram with straight lines. We physically show you the trajectory. We show you it, and it will overshoot the points and come back because of filtering, which is to be expected. But Tetra can have a 3.2 dB crest factor. Well, 3 dBs is double the power. So your 40 watt average output now becomes 84 watts peak. Okay. So imagine if you had 4 base radios running at 40 watts each, average power, potentially you could see 336 watts peak. Okay. So just bear that in mind when you're testing base stations. Think about the crest factor and the peak power. Think about multiple base radios all coming to that transmitter port. Okay. So always think about having a power attenuator with you if you're testing base stations. We have auto test capability, like I said, for Tetra MS. It's quite a simple thing. It was ported over from the old Marconi 2968. Only works in MS, nothing else. But we also have auto test 2, which is much more powerful. Now I'm going to jump quickly through the video, but you can see here we've basically done a lot of measurements ourselves. All you have to do is key the radio or answer the call, and that's it. And then we take control. We can move traffic channel, we can change power levels, we can do all those measurements. Okay. Auto test 2 has a lot more capability. So for example, with I'm going to again jump through here. Here we're actually reading the serial number and model number out of the radio and its capabilities, what software it has inside. We're doing measurements. Okay. Look how long that took. This is a Motorola MTP-850 radio. And by the way, this can be fully encrypted and we can still test it. Why? Because we're using manufacturer's engineering commands. We are not using service commands. Okay. And we have equivalents for example, Airbus and Motorola Tetra base stations. And again, this is an MTS base station, just one base radio. So if you have 4, you have to do this 4 times. But look at that, 2.5 minutes. And that's test three transmit power levels and 1 receiver. I could test all 3 receiver paths as well if I wanted to. So 3 transmit power levels and 1 receiver, but at 3 different power levels, all in 2.5 minutes. Okay. So you see here, it says Cassidian on my test set. I need to get that updated, but Airbus as well. We have TB3, TB2, for example. But I will jump through this just to finish up. Just touching on the 8800SX 3550R, and this does go back as well to the original 8800 model, 8800S, and the plain 3550s. You have some limitations. So they will both support Tetra base station T1 mode, but they don't support Tetra MS or Tetra direct mode. 8800 has auto test capability, but not for the Tetra radios at this time. 3550 does not have any auto test capability. Okay. Just like the 3920, we can use it for drive testing. We can use these for indoor measurements as well with the TRX Neon software. We can support both pulse sync and auto sync modes, but we only have the T1 Type 7 test signal. Okay. Unlike the 3920, which supports all the ETSI test signals, we only have the one that is the one that 99% of the people are using anyway. Okay. So with this video, I'm actually on the left, I'm actually typing commands from a computer into the base station. Here's my receiver measurements. Okay. And you'll see now I've put minus 118 dBm into the base radio. Whoops, apologies. And you'll see here it's actually read minus 118 dBm, and I've got 1.5% bit error rate. Okay, at high level, minus 76 dBm, I've got 0% bit error rate. Okay, some other videos I'm not going to go into now, but just to summarize, the 3920 performs ETSI compliant Tetra measurements, as really do the other 2 test sets for base station T1 mode. Okay. We have auto test 2 capability, and Tetra radios are supported on those products. For auto test, I'm happy to give you, if you want, a test script that I originally did for a SUIVRE radio that you can very easily use for any other radio. Okay. The automated portables, we've only got the MTP850 in series. I personally would like to add the newer Motorola radios and other manufacturer radios, and for that we need you as the customers to push back onto those manufacturers. Say, guys, come on, we need these guys at Viavi to do this for us. Okay, push back on the manufacturers so they work with us. We do this with all of the other standards, your DMR, P25, NXDN, for example. Fully automated base station testing or commissioning tests. So you don't need the engineer's computer. We do that for you. We become the computer. We control the base station as well as a test set. And you could write your own tests using the Ethernet remote control on any of the test sets. And a final note there, do not forget to include the cable loss in the RF measurements. That will be your biggest problem otherwise. Okay. So thank you. I'll throw it back to Francesco now if we have any questions.
Hi. Barry, thank you very much for your presentation, very in-depth presentation. Yes, we have several questions. They started to come in from the beginning of your talk. I can pull some of them. One is, for example, please advise how to detect Tetra base station and MS bad synchronization issues, decreasing coverage radium, especially when Tetra base station synchronization is switched from E1 to IP synchronization by NTP or PTP protocols.
Okay, so the easiest way to check the timing, I know most people use GPS, or should I say GNSS systems, for timing synchronization on their Tetra base stations and Tetra networks. The main country that doesn't do that is China. Okay, they took the decision, we don't trust the American GPS system, therefore we'll use network timing. As network timing's improved, I mean IP network timing, Ethernet timing, as that has improved, more people will use that going forward because of the issues with GPS spoofing and jamming. Sorry, GNSS, I shouldn't just limit it to the US system. Could be any system that's spoofed or jammed. So a lot more people will start using IP network timing. Or they use that now anyway as a fallback method. So if the GPS failed or GNSS failed, they would drop back to network time anyway. You can actually check that to some level with the test set, because in the test set, we run off a 10 megahertz oven controlled reference, which is usually pretty good. Not as good as a GNSS system, but pretty good. What you can do then off air is you can sniff a base station, a channel, and when you decode it, you will get the frequency error. So that frequency error, typically, if it's out by, say, 8 hertz, that's actually the error in our OCXO, our 10 megahertz OCXO, translated up to whatever, 380 megahertz. So if you take 10 hertz error divided by 38, that's the error in our 10 megahertz reference, okay, because it's at 380 megahertz. So you could actually check the timing of the infrastructure by looking at the frequency error on the test set. Of course, test set to test set may change a little bit, or you can even calibrate the test set in your lab using, a rubidium standard, for example. Say, okay, I know my test set is out by 8 hertz, so if I measure a base station, it's out by 8 hertz. I know the base station is perfect. If my test set says 12 hertz, I know my base station is actually off on timing a little bit. Okay, so that might be a simple method to do that.
Okay, Barry, thank you for this answer. One easy one. On slide 20, you identify the radio manufacturer just by the power ramming profile. This person is asking if we have something or a chart identifying the radio for these different manufacturers? They need to buy a Ranger in this.
Yeah. We have a nice big system. You guys can buy a broadband system from our sort of military portfolio, shall we say? Not purely military, commercial as well. But yeah, we could characterize things in there and work out a lot more than we can do here with the test sets. A lot of my knowledge of which user or which radio it is, even if it was in a box or a black bag and I didn't see it, whether it's a base station, mobile or portable, I'm pretty good at picking out some of the manufacturers now because of the characteristics of their radios. However, you could have another manufacturer's radio that has slightly poorer performance than they would normally have, and that could then look like one of those other manufacturers who have done it deliberately, to save a little bit of battery power or to increase talk time or to try and improve something else. So it's quite interesting now. In the good old days of radios 20 years ago, most things you turn a little screw and you tune things up that way. Now it's all done with software-defined radios and DSPs. So like I said, even the ramp profiling is generally software controlled these days in the radios. So yeah, I can see some of the features on radios, and I can very quickly tell you whose base station or whose portable or mobile it is. But we do have other systems that will do that in a much better, efficient way for you. So if anyone here is from the military or government or the bigger commercial organizations, they might be interested in that.
Yeah, in this case, just ping to us and then we'll be able to respond to you directly.
Mm-hmm.
One more question. Can a 3920B work with any Tetra radio or base station? What if it is encrypted?
Okay, so yes, it will work with any mobile, portable, or base station, at least as far as I know, and I've been working with this test set for over 15 years now, and previous to that with the Marconi test set and the Wiltec testers. With encryption, no, we don't have encryption on the test sets. Interestingly, for P25, for example, we do have encryption capabilities, both AES and DES. Some of that is export controlled out of the US. For Tetra, there is no encryption capability. And it's a decision we made many years ago at the start, because some countries, knowing that the initial market was all public safety, not commercial initially, some countries, and some of them quite influential around the world, said that if there was encryption capability on the Tetra system, then the product would either be export controlled or would be blacklisted in that country. And multiple countries were telling us this, so we took the decision not to include encryption. So a couple of ways around that: you have a clear channel on the radio that's programmed in and just left there that users don't normally see or use, but we have access to it. That does leave you with a potential security hole. That's been recognized over here, for example, with GCHQ in the UK. That would be a security risk on the emergency services network. Potential risk. There's lots of other risks. You could have a fallback mode enabled, so if there are no encrypted channels available on your network, it will automatically fall back to unencrypted. Again, that's a security risk, but it's good for us. I've actually seen that in a Middle East network where police were talking and it was unencrypted. Now, it was Arabic, so to me it was encryption. I don't understand Arabic, but it was plain voice Arabic. So when the customer found out, they got very upset. I found the problem for them, and they went to their supplier. A group of them went to the supplier very quickly and demanded this was fixed. And the third way you do it is you have to reprogram the radio. So that's the least preferred method. Okay, but encryption is always an issue with national security and leaving a method open for someone to attack your network. So it is quite a hot topic, especially with cybersecurity these days.
Okay, Barry, thank you very much. I believe that We have used 5 minutes more than our time. I believe that it's time to stop. We will respond to all your questions directly with separate emails. We will contact you, and then we are going to send you the registration, the link of registration of this presentation within 48 hours, roughly. This will be the average. I would like to thank you, everybody, and we would like to see you next time to the next session. Ber, do you want to say the last word?
Just thank you everyone for listening to me once again. I hope you enjoy the webinars. Apologies, it seems to always be me doing them in EMEA, but I do have a good broad depth of knowledge on both these public safety type systems and commercial systems, and also the military systems. So at least if you have some in-depth questions, I'm probably the right guy to answer them. So again, thank you very much for attending, and we hope to see you at the next webinar. Bye-bye.
Bye-bye.